Question number 13. A person holds a bundle of hay over his head for 30 minutes and gets tired. Has he done some work or not? Justify your answer. Okay, so though he gets tired, we know that in science we define work as a force times the displacement in the direction of the force. So since this person has not moved, since the displacement is zero, no, there is no per science, per physics, per the definition of work in physics, the person has not done any work. An electric heater is rated 1500 watts. How much energy does it use in 10 hours? So we know that, since it's watts, we know that, it's the power. Power is equal to energy of work done or consumed by time. And we know that it's given that it is 1500 watts. So energy per second is 1500. And energy in 10 hours is equal to 1500 into 10 times 3600 seconds. And it's all in joules. So it comes down to be around 54,000 kilojoules. Illustrate the law of conservation of energy by discussing the energy changes which occur when we draw a pendulum bob to one side and allow it to oscillate. Why does the bob eventually come to rest? What happens to its energy eventually? Is it a violation of the law of conservation of energy? So there are multiple questions here. And so this is a very interesting scenario to understand, and probably a very good example to understand mechanical energy. So a pendulum. So the situation is that you have a pendulum, and you pull the pendulum's bob to a certain height, and let's consider that height to be let's consider if the pendulum is here, and if this is the original state of the pendulum, and let's say that we raise it to a certain height. So this part is what is the difference in the height, right? So let's consider this to be h. And when you let the pendulum oscillate, it will keep oscillating this way, right? So by the time you start to, by the time you pull it up to a certain height, right, it only has the potential energy, right, which is mass times the gravity times the height. The height here is the height, the difference between its original state and its current state. So this difference is what is the height here, and that is how you would calculate the potential energy of the pendulum just before it starts to oscillate. And just before it starts to oscillate, the kinetic energy is going to be zero, right? Now, and what happens when you let it oscillate? It will start to oscillate, and as it starts to oscillate, its kinetic energy will increase, and it will take that kinetic energy from the potential energy only. So right at the right out here, when it is traveling, when it hits this particular point, here the height is zero, right? Because the difference is, when the pendulum, after you start to oscillate, and when it comes here, at this point when it is about to move, the height is zero, and for that brief moment, the potential energy is going to be zero, and the entire energy would have been kinetic energy, right? So at this point, the kinetic energy will be the original potential energy completely. And by the time it reaches this point, it means that it would have once again, it would have acquired the same potential energy, because it would have acquired that displacement of h. So which means it would become that your potential energy would be its original potential energy. And at this point, it will start to come back, right? Which means that it's no more moving. So at that brief moment, its kinetic energy is going to be zero. So it always oscillates. As the pendulum oscillates, it starts with a complete potential energy and zero kinetic energy, and by the time it reaches the other end, it once again becomes the entire thing becomes its potential energy, and its kinetic energy becomes zero. But during the transition, the kinetic energy is increased, and the kinetic energy is the maximum at the midpoint, right at the midpoint, right? So that is how the energy transfer happens in the pendulum here. Now, the point here is so this whole energy, the pendulum does come to a rest at some point in time, right? So the question is, why does the bob eventually come to rest? It comes to rest because of the resistance of the air particles here, right? Because we are considering this whole medium to be air, right? And air has particles, and that offers some resistance. And we saw this in the earlier chapters of buoyancy and force. And it is that resistance which which causes the pendulum to slow down, right? Basically, that energy, the original potential energy, is dissipated or transferred into those particles, right? And that is how it eventually comes to rest. And over a period of time, yes, what happens to its energy? The energy is completely dissipated into its air particles, and that is why it comes to rest. And so this doesn't mean that the law of conservation of energy is invalid. Yes, the law of the energy is still conserved, just that the energy is now transferred to the air particles around, and that is how the pendulum comes to rest eventually. In fact, if you do this experiment, if you let this pendulum oscillate on a medium that is free of any air particles, in complete vacuum, the pendulum will continue to oscillate forever by Newton's first law, right? Because it is in motion, it will continue to be in motion throughout. Question 16. An object of mass m is moving with a constant velocity v. How much work should be done on the object in order to bring the object to rest, right? So because this object is moving, we know that it has a kinetic energy which is half mv square. So the amount of work that needs to be done to bring it to rest should be the negative of it, right? To really bring it to rest, you have to there has to be the work that is needed to be done should be in the opposite direction in which the object is actually moving. It is like applying brakes on your car that is moving with a certain velocity until you and the work that you need to do should be equal, but in the opposite direction. The force has to be in the opposite direction of the opposite direction of the movement of that particular object, and until it equals this kinetic energy, your object will not stop, right? So the work that is needed to bring it to a full stop is actually minus half mv squared. At least that much of force you'll have to give it to. You have to give exactly that much amount of force to bring it to a full stop. If you give a bit more than this in the opposite direction, the object will start to move backwards. So the force, the work to be done is minus half mv squared. 17. Calculate the work required to be. Oh, sorry, this is what we just saw. Okay. No, it is this one. So okay, calculate the work done by calculate the work required to be done to stop a car of 1500 kgs moving at a velocity of 600 kilometers per second. Okay. So this is the same question related to the earlier one. So we can use the same logic here to actually quantify this. So we saw that the work to be done is minus half mv square to bring a moving object to a complete stop. And in this case, the moving object has a mass of 1500 kgs and it's moving at a velocity of 60. So minus half mv square is minus half into 1500 into 60 into 5 over 18 squared. So this is where we are converting this into meters per second. So that is why you have this logic here. We are converting 60 kilometers per hour into 60 meters into certain meters per second. So that's why you have this. So this comes down to minus 208,333.33 joules. If you do this calculation, you'll arrive at this number. In each of the following, a force F is acting on an object of mass m. The direction of displacement is from west to east, shown by the longer arrow. Right. Observe the diagrams carefully and state whether work is done by the force is negative, positive, or zero. Okay. So in all the three scenarios, we see that the object is moving from west to east, that is from left to right. Right? In all the scenarios, the object is actually moving from left to right. However, the direction in which the force is applied is different. So in this case, the direction is applied like this. Yet the object, so it is perpendicular to the direction of displacement. So the displacement in the direction of this force is zero. So which means that the work done is zero here. However, in this case, the direction of the force is in the same direction of the displacement, so it is a positive acceleration, right? So when you keep applying this force to an object that is moving in this direction, it will move faster. That is positive acceleration, which means that the work is also positive. In this case, you're applying a force in the opposite direction of the direction of displacement, which means that the object will undergo negative acceleration, which means that your work is going to be negative. Right? So that completes this. Sony says that acceleration of an object could be zero even when several forces are acting on it. Do you agree with her? Why? Okay. So Sony says that acceleration of an object could be zero even when several forces are acting on it. We know that when a force is applied on a particular object continuously, it will tend to accelerate, right? And if multiple forces act on the same object, it will definitely tend to accelerate. But if multiple forces act on the opposite direction of that particular object, if you apply the same force, maybe the object will not accelerate. Right? So in a sense, for an object to accelerate, it is not just that you have a force acting on it. We learned that the net unbalanced force, has to be greater than zero for an object to accelerate. Right? If the forces are acting in opposite directions such that the net unbalanced force is zero, then the object will not accelerate. Right? So Sony was right. Yes, if the forces are acting in the opposite direction, if the same forces are acting in the opposite direction, and if the net unbalanced force is zero, then the object would not accelerate. Find the energy in kilowatt consumed in 10 hours by 4 devices of power 500 watts each. Okay. There are 4 devices, and the power of each device is 500 watts. So the power of 4 devices is 500 times 4, which is 2000 watts, which is 2 kilowatts, right? So this is the power of 4 devices. So the total energy is equal to power times the time, right? And which is equal to 2 kilowatts times 10 hours, and which is equal to 2 kilowatt hours. So this is what is your total energy, which is 20 kilowatt hours. Freely falling object eventually stops on reaching the ground. What happens to its kinetic energy? Okay. So this is an interesting question. So your object that was held at a certain height had all potential energy. When it was hanging, it was all potential energy. Kinetic energy was zero. When you dropped it, the potential energy started reducing because of the reduction in height, and that reduction in potential energy resulted in the kinetic energy, right? Got transformed into kinetic energy. Just before hitting the ground, the potential energy would have been very close to zero, but the entire thing would be a kinetic energy. But what happens after hitting the ground? You're likely to hear a huge sound, right? A thud you're going to hear. So the entire energy is converted into sound energy. In some cases, maybe it is converted into heat energy also, right? So that is how the law of conservation of energy is also upheld. Energy is not destroyed. When an object falls on the ground and when nothing happens to the ground, because the earth is huge, and right, even though you drop a huge iron ball, it is the weight of the mass of that iron ball is negligible when compared to the total mass of the earth. So that's why nothing happens, but still you will hear a sound, and that's the transformation of that energy. So the mechanical energy got transformed into sound energy and possibly to some heat energy. Maybe the part where it hits, you keep hitting it, maybe it will get warmer as well. Right? So that is also possible. So I think with this we have completed all our questions part of the exercise section, and in another video let's talk about the next concept of sound. Thank you.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share and subscribe this with your friends. Thank you.